Well, welcome back. I was going to help you guys out with another helpful hint video for your next homework set, which is chapter 8. And so, homework number 8, that is. And so let's take a look at some of the questions that we're having to deal with here and see if I can give you guys some helpful hints and stuff. This first one is, let R be a commutative ring and let Q be a fixed element. Prove that the set Q, which is equal to the elements little r from big R, such that R equals T times Q for some element T in R, is an ideal of R. Now, my recommendation for this one is for you to go back and look at the lecture video for section 6.1 and 6.2, and particularly 6.2, the idea of a principal ideal, and focus on that, but I restructured Q a little bit. Now, first off, let's talk about generalities here. First thing, I gave you a commutative ring. Merry Christmas. So you don't have to worry about X times R and R times X type thing here. We know your definition of an ideal with the third property. But the real deal is you have to follow along from theorem 6.1. And according to theorem 6.1, what are the things that you have to show? Number one, you got to show it's non-empty. Which means I got to show, now look at the Q. To be inside a Q, this is where you come from and this is what property you have. So to be inside a Q, remember R was a ring and Q is a fixed element in R. So to be inside a Q, you got to come from R and you have to look like, R has to look like somebody, a new element, great time for subscripts, times Q. Remember, Q was announced to be the fixed element, and it's in the back. So order matters on this thing, but it is a commutative ring, so again, Merry Christmas. So here's the idea. To show it's non-empty, I've got to show that 0R is an element of Q. Now, why would 0R be an element of Q? Well, one, R is a ring. Two, since it's a ring, 0R is an element of R. Three, who does 0R look like in terms of times Q? Well, 0R would actually be equal to 0 of R times Q. So because of that structure, 0 times anybody is 0, that's automatically going to put 0R element of Q, and Q is non-empty. The second thing you've got to do is you've got to show it's closed under subtraction. Closed under subtraction, closure, if you will. Which means that we're going to let my favorite two guys, X and Y, be an element of the set Q since it's now non-empty, and then I'm going to have to show that X minus Y is an element of Q. Now, look at your ring structure. To be inside a Q, this means X and Y are elements of R, and there exists a T1 and a T2 from R. Got to declare that element before you use it, such that X is equal to T1 times Q and Y equals T2 times Q. So now I want to talk about the subtraction. So go in there and talk about X and Y as an R, and X minus Y as an R. And X minus Y is going to be equal to T1 times Q minus T2 times Q. And I believe you can be able to factor out a Q in the back and then talk about what the deal is about the T1 minus the T2 and where does that come from. So then, if you, again, focus on the set Q. To be in set Q, you got to focus on three things. The elements have to come from R. The elements have to be equal to another element times Q in the back, where the element in the front came from R. And then for part number 3, this is truly your definition of an ideal part, which is that we're going to, as X is an element of Q, we're going to let little r be an element of big R. Okay? Now, to be X be an element of Q, there also exists, there's that T1, there's that T1 element of R, such that X is equal to T1 times Q. So X is structure, R is arbitrary. We want to focus on X times R. Well, X is from R, and R is from R, so X times R is an R because that's a ring, and X times R would be equal to when you substitute T1 times Q times R, but we got to get this structure. Q's got to be in the back. But I want to remind you, R is a commutative ring, so order's not going to matter. So you can move this thing around and put the Q in the back, and then you can talk about the element in the front coming from R. So, and because it's a commutative ring, remember X times R is going to be equal to R times X, so you got both ways you're going to have to show is an element of Q. Then you can quote your theorem 6.1. So again, I'm being very vague on this because I want you guys to structure it a little bit better, but the other hint is also the lecture notes. I did a problem very similar to this, so go back and look at that. Here's another problem in section 6.2 that I did, but I did it the other direction. Let's pay attention to what this problem asks for. It says that R and S be rings and phi is a surjective homomorphism. If means given. I'm going to give you an ideal of R. I want you to prove that where the guy maps to J by definition is all the elements H and S, such that the H is equal to phi of K for some K in M is going to be an ideal of S. And I need this idea of surjective because if I start picking myself arbitrary elements over here in S, I got to make sure somebody's going to map to them. And surjective actually does that. So I want to show that J is an ideal of S. Again, I'm going to quote theorem 6.1. I got to show it's non-empty. But again, remember, I'm giving you that, so lots of givens. Let's start off with the givens. What are we given? We are given that R and S are rings. But notice I did not give you they were commutative rings, so this is going to be a longer proof. I've also given you that phi going from R to S is a homomorphism. Okay? And one other thing I gave you, M is an ideal of R. You need that structure. Pay attention to M being an ideal of R, and so you're going to use that to show that J is going to be an ideal S. Remember, under homomorphisms, it's property preserving, so ideals map to ideals. So, also remember, not just any homomorphism, I gave you a surjective homomorphism. So that means it's on to. So anybody I pick over an S, you know there's going to guarantee there's a dude that maps to it. So, first thing you got to do is from theorem 4.1, you got to show it's non-empty. And the reason why it's non-empty is 0 and S is going to have to be an element of J. Now why is that? Well, remember R and S are rings, so automatically 0R is an element of R and 0S is an element of S. And also remember that phi of 0R is equal to 0S, and again I want to quote that theorem that you should have memorized by now, theorem 3.10, but also M is an ideal of R, which automatically puts 0R inside of M. Now, again, the key to this stuff is paying attention to your set structure. To be inside of J, you got to come from S. 0 and S comes from S. You got to have the property that the same element, H, in this case, 0 and S has to be equal to phi of somebody. 0 and S is equal to phi of 0R, where that somebody inside the parentheses, 0R, came from M. So all three things have been satisfied. That puts 0S inside of J, and J is non-empty. Of course, you've got to write all this stuff up in the proper format. And on this one, I didn't need any surjective part or anything like that. Where's the surjective going to come in at? Well, the next thing you've got to show is closure under subtraction. This is my scrap sheet, so I get to kind of basically abbreviate everything here. Closure and subtraction, so we start with our standard, let X and Y be an element of J. Here's the hint. To be inside of J, where do you come from? This implies that X and Y are elements of S. Remember, write proper English. This is my scrap sheet of paper. And there exists, okay, because phi is surjective, there exists, because phi is surjective, elements H1, great time for K1, K1 and K2 in M. Again, looking at my structure up here, K1 and K2 in M, such that X is equal to phi of K1 and Y equals phi of K2. Again, where most students screw this stuff up at, they'll put phi on the wrong side. They'll do phi of X equals K1, phi of X equals K2. No, K1 and K2 come from M, which is a subring of R. They're inside the parentheses. What's outside the phi is going to be elements of S. X and Y come from S, so they're going to be equal to the phi guys. So now you've got to talk about X minus Y. X and Y are in S. X minus Y is going to be in S. X minus Y is going to be equal to, by substitution, phi of K1 minus phi of K2, and then that's equal to phi of K1 minus K2 again by my famous theorem 3.10. Homomorphism theorem is 3.10. And then K1 minus K2 has got to be an element of M because K1 and K2 are in M. All that together is going to put X minus Y in J. And then the third part is you've got to talk about, well, I keep going that as X is an element of J, you need to pick let little s, so arbitrary, he's just going to be called little s, element of big S. As phi is, again, surjective homomorphism, then there exists guaranteed little r element of big R such that S is equal to phi of R. Again, I need that surjective because I picked a dude over an S. And if phi was a surjective, I could have picked an arbitrary dude that nobody mapped to because nobody liked. Well, in surjective, it's on to everybody over an S gets mapped to. So I needed that surjective to be able to guarantee there's going to be an R in R that maps to it. And again, from our other definition, you know, there's this K1 element of M such that X equals phi of K1. Now go and multiply X times S and S times X, because you got to do both ways. X times S, and you got to do S times X, because I did not give you a commutative ring. But again, the structure is going to be very similar to what I did in terms of the notes you should be taking in section 6.2. Now, number 3 here is obviously a very short proof because I didn't give you much room on it. This is the definition, and it's supposed to be very straightforward. I'm just trying to work these definitions for you. Let I be an ideal of a ring R, and let B, C, and F be elements of a ring R. Prove that if means given, so we're given, that B is congruent to F mod I, and F is congruent to C mod I. Now, where most people are going to screw this up as they're going to tell me, well, by definition of congruence, modulo I, and that part you're right, what do you have? And they're going to tell me I divides B minus F. No, there's no dividing in ring structure. This is now ring structure. This is modulo an ideal. Remember your definition of congruence modulo I means that B minus F is an element of I. And F minus C is an element of I. So there may be a little I that you can add, a little I1 and I, and a little I2 and I, such that B minus F is I1 and B minus F minus C is I2. You can write it like that, but I don't even think you need to go that further. These are, the difference is elements of I. I is an ideal, okay, it's also a subring with extra properties of that multiplication. One element in I times any element in the ring is back inside the I ideal there. So I want to show B is congruent to C mod I. What does that mean? So by definition of congruence, you cannot abbreviate, I can, that I want to show that B minus C is an element of I. Well, these two elements are an I. How can I put these two guys together? Remember, I is a subring also, so it's got some wonderful closure properties. How can I put these two guys together to be able to pretty much get just a B minus a C. That's the trick. And because it's an I, since I is an ideal, which means he's also a subring, but he's an ideal, he has closure properties. Now, these last two are actually from chapter 5. So again, I want you to play around with this thing here. And again, I give you something nice. Z2 adjoin X. Z2 are the elements 0 and 1 equivalence classes. The polynomial is x cubed plus x plus 1. So these are going to be the classic equivalence classes from chapter 5, modeled out by x cubed plus x plus 1. It's going to have a particular remainder structure. What would that structure be? Where you A, B, and whatever, C or whatever, A all have to come from Z2. So not only figure out how many there are, you need to be able to write them all out. And then once you've written them all out, what kind of ring is it going to be? You've got to figure out whether that polynomial is irreducible or reducible by checking to see what kind of zeros you got. So again, this is a short video because I did a lot of work on those section 6.1, 6.2. This is chapter 5.3-ish stuff here, but I just want to practice that again. So again, study this stuff, and this hopefully will help you out in your guidance in terms of being able to write this stuff up and prepare you guys for, as these homeworks are supposed to do, for your next test. So thanks.